So if you take a standard 1-inch cube of A36 structural steel.
Which is what about the size of a piece of candy?
Yeah, exactly. Like small enough to easily swallow. And if you take that tiny cube and you hang a fully loaded 36,000-pound school bus from it,
Right.
that little piece of metal won't break. It won't snap. I mean, it won't even permanently stretch out of shape at all.
It's pretty wild to think about.
It is. The bus just hangs there, suspended by this tiny little cube.
And, you know, the crazy part is the moment you unhook that bus, the steel cube just snaps back, like perfectly back to its original dimensions.
Wow.
Yeah, the molecular bonds inside that iron and carbon matrix, they just absorb the weight, stretch imperceptibly, and then recover. Like nothing ever happened.
It's hard to wrap your head around. But that kind of invisible structural resilience is happening all around us, like constantly.
Oh, absolutely. Every single day.
Right? Like every time you cross a bridge or park in a concrete garage or honestly just sit in your living room, there's this violent, silent battle happening inside the walls and the columns holding up your world.
That's a great way to put it. A silent battle.
But the thing is, to most of us, that battle is completely invisible. We don't speak the language.
No, not at all.
If you look at a structural analysis report or, a building blueprint, you are immediately hit with this absolute alphabet soup of units.
Oh, yeah, it's totally overwhelming.
You see things like N, KN, MPA, KIPS, KSI, PSF, KLF. It just looks like abstract, high-level theoretical math.
It really is an intimidating wall of letters if you aren't initiated, because an engineer looks at those letters and sees like a vivid three-dimensional simulation of how a building breathes and bends.
Right.
But without the vocabulary, it's just ink on a page.
Well, that's exactly why we're here today. We are translating that alphabet soup into physical reality.
I love it.
We are talking directly to you, the listener, because maybe you want to know the true meaning of these units. Whether you're trying to read construction documents, prepping for a project, or just intensely curious about the hidden forces keeping the roof over your head.
Which is a very cool thing to be curious about, by the way.
Totally. So we are going to break down the barrier between the math and the material. By the end of this deep dive, you won't just know what a 50 kip load or a 4,000 psi concrete spec is on paper.
Right, you're actually going to feel it.
Exactly. You'll be able to feel exactly what that weight and pressure represent in the real physical world.
And to do that, we're diving deep into the governing documents of the physical world. We're pulling from international building codes, specifically the Eurocodes.
Which dictate how environmental forces act on structures, right?
Yes, exactly. Plus, we're tearing into structural mechanics, lectures, concrete strength specs, and standard contraction tables from the American Institute of Steel Construction.
And we even have some practical handwritten field notes from an active engineer, which I love.
Yeah, those are gold. It really grounds it in everyday practice.
But, we aren't just going to memorize conversion tables today. We want the physical truth. So to build that understanding, we kind of have to start at the absolute foundation of physics.
We do, the very bottom.
Because before we can talk about a skyscraper resisting the wind, we have to understand what it actually means to weigh something.
Right.
Because in everyday life, we completely blur the lines between mass and weight. Like you step on a scale in your bathroom and say, I weigh 180 pounds, or I weigh 80 kilograms.
Yeah, we use them interchangeably.
But in structural engineering, if you confuse mass and weight, your building comes down.
It is arguably the most common and dangerous misconception out there. In the engineering standards used in the U.S., what we often call English engineering units, the pound actually leads a double life.
A double life. Okay, explain that.
So there is the pound mass, which is denoted as pound, and then there's the pound force, denoted as BF.
Okay.
They measure two fundamentally different realities of the universe.
Okay, let's pull those apart for a second. If I have like a sack of cement, the mass is the actual physical stuff inside the bag, right?
Okay.
The dust, the crushed limestone, the atoms.
Yes, exactly. Mass is the unchangeable quantity of matter.
Unchangeable.
Right. So if you take that bag of cement and put it in the trunk of your car, it has the same mass. If you load it onto a rocket and shoot it into deep space where it's just floating weightless in a vacuum,
It still has the exact same mass.
precisely, it still has the same number of atoms. That is the pound mass.
But the pound force is what happens when that sack of cement actually interacts with a planet.
You nailed it. Force is an interaction. Gravity is pulling those atoms toward the center of the Earth. So a pound force is the specific amount of physical push or pull that standard Earth gravity exerts on 1 pound mass.
So because we all just happen to live on the surface of the Earth where gravity is practically constant everywhere,
Oh.
1 pound of stuff happens to exert exactly 1 pound of force pushing down on the floor.
Exactly. It's a 1-to-1 ratio purely by the geographic accident of where we live.
Which is why we get lazy. We just call both of them pounds.
That is the exact trap. Because if an engineer were designing a habitat for the moon, where gravity is, only a fraction of what it is here, that 1-to-1 ratio disappears completely.
Oh, wow. Yeah, of course.
The pound mass stays exactly the same, but the pound force drops drastically. A structural column on the moon doesn't need to be nearly as thick to hold up the exact same mass of material.
That's fascinating. Now, the metric system handles this a bit more cleanly, right?
So much more cleanly.
The base unit of mass in the metric world is the kilogram. And we do a lot of converting between the two systems. Like a staple conversion is moving from kilograms to pounds.
Right. And to be precise, 1 kilogram of mass is equal to about 2.205 pounds of mass.
Okay, 1 kilogram is 2.205 pounds. I'm going to lock that in.
And when engineers do these cross-system conversions, they rely heavily on dimensional analysis, usually using what's called the unit fraction method.
I'm actually really glad you brought that up because instead of just memorizing whether to multiply or divide, dimensional analysis feels more like a philosophical tool.
It really is. How do you visualize it?
Well, you're setting up a fraction where the top and the bottom are physically identical realities, just wearing different outfits,
That's a perfect way to conceptualize it. If you have 15 kilograms and you multiply it by a fraction where 2.205 pounds is on the top and 1 kilogram is on the bottom.
You are technically just multiplying by 1.
Exactly. You aren't changing the amount of physical stuff. You are just forcing the mathematical label of kilograms to cancel itself out, leaving you with pounds.
It's like an error checking mechanism.
Completely. If the units don't cancel properly, the engineer knows instantly that their math is flawed before they even look at the final number.
But wait, that still leaves us with mass. If the kilogram is just a measurement of stuff, what is the metric equivalent of the pound force? Like, what is the actual unit of push and pull?
That is the domain of the Newton, abbreviated with a capital N.
Okay, the Newton. I really want the absolute true meaning of a Newton. We hear the name constantly, Isaac Newton, gravity, the apple falling on his head. But if I'm looking at a blueprint, what exactly is 1N?
Well, if you look at the strict classical physics definition, 1 Newton is defined by motion. Force equals mass times acceleration.
Right, F equals ma.
Yeah. So 1 Newton is the exact amount of force required to accelerate a 1 kilogram mass by 1 meter per second every single second.
Okay, I have to pause you there because that definition has always bothered me.
How so?
Accelerating a mass by 1 meter per second squared feels like a high school physics lab,
Yeah.
with frictionless carts rolling down little ramps.
Yeah.
It does not feel like a construction site. When I am standing in a parking garage, nothing is accelerating.
Let's hope not.
Right. The concrete isn't moving. The cars aren't falling. It is entirely static. So how do I translate a Newton into a static feeling? Like, how do I feel a Newton in the palm of my hand?
Okay, I love this question. To feel it, we have to bridge the metric force back to the force we already understand intuitively. We know what a pound of force feels like.
Right.
According to the conversion standards, 1 pound force is equal to roughly 4.448 newtons. We generally just round that to 4.45 for practical, everyday visualization.
Okay, so 1 pound of gravitational pull equals roughly 4.45 newtons of pull.
Yes. So imagine you go to the grocery store and pick up a standard 1 pound block of butter.
Okay, I've got the butter.
When you hold that butter steady in your outstretched hand, you are feeling Earth's gravity pulling that mass downward. Your muscles are actively pushing up with 1 pound force to keep the butter from falling.
Makes sense.
Because of that conversion, the static push your muscles are exerting against gravity is exactly 4.45 newtons.
Oh, wow. That completely changes how I visualize it.
Yeah.
Because if 4.45 newtons is a whole block of butter, then a single Newton 1N is tiny.
It is very tiny.
It's less than a quarter of a pound. It's literally the weight of a medium-sized apple resting quietly in my hand. That's it. That's the true meaning of 1N. It is an incredibly small amount of physical force.
It is minuscule. And that realization forces a massive shift in how we approach structural engineering.
How so?
While if 1 Newton is just an apple and 1 pound is just a block of butter, you cannot possibly design a 50-story steel and glass high-rise using those base units.
Oh, I see. You'd be dealing with billions of apples. The blueprints would just be a sea of zeros.
Exactly. It would be impossible to read, and worse, it would practically guarantee a catastrophic clerical error where someone drops a zero and suddenly a support column is 10 times too weak.
Which is exactly why engineers had to invent new vocabulary. They had to scale up from the palm of the hand to the scale of the city.
Precisely. And in the American system, that scaled-up unit is the kip.
The kip. Now, I had never encountered this word outside of engineering. What is the actual meaning of a kip?
It's actually a linguistic mashup. It's a portmanteau of kilo and pound, kilo meaning 1,000. So 1 kip is exactly 1,000 pounds of force.
Kilopound. Kip. That is so simple.
It was born entirely out of practical necessity. In the days of hand-drafting blueprints, writing out 50,000 pounds repeatedly across a massive architectural drawing was tedious, and it was messy.
Yeah, too many zeros.
Writing 50 kips, or simply 50K, is clean, efficient, and leaves far less room for interpretation.
And the metric system just applies its standard prefixes to the Newton, I assume.
Yes, the metric equivalent is the kilonewton, abbreviated as KON. It is simply 1,000 newtons.
Okay, so if we cross-reference those handwritten field notes we have, we see the conversion play out. The notes say 1 pound equals roughly 0.00045 kilonewton. So if we scale that up, 1,000 pounds, which is 1 kip, equals about 4.45 kilonewtons.
Exactly. The math stays perfectly consistent. So now we have our heavy building blocks. We have scaled up from the apple to the boulder, essentially.
Well, let's make that boulder tangible. We promise to deliver the real-world feel of these numbers to you, the listener.
Let's do it.
When a structural engineer casually mentions that a standard interior concrete column in a building is supporting a 50 kip point load,
Yeah.
what does 50 kips physically mean? Like, what is the reality of that weight?
Okay, we do the math first, then we build the picture. 50 kips. We know 1 kip is 1,000 pounds. So 50 kips is 50,000 pounds of total force.
Right, but 50,000 pounds is still a number most human brains just can't instinctively process. We need a physical comparison. Let's convert it to tons.
Good idea. A standard short ton in the U.S. is 2,000 pounds. So 50,000 pounds divided by 2,000 gives us exactly 25 tons.
Okay, 25 tons. Now think about an average mid-size sedan on the road, like a Honda Accord or a Toyota Camry.
Yeah, those cars weigh roughly 1.5 to 2 tons each.
So let's use a slightly smaller car, right around that 2,000 pound mark.
Okay. To visualize the 50 kip load on that single concrete column, you have to imagine taking one of those cars and parking it right on top of the column.
Just balancing there.
Yep. Then a crane lowers a second car directly on top of the first, then a third, then a fourth.
You just keep stacking them. Higher and higher, crushing the suspension of the cars below them until you have a vertical teetering tower of 25 cars stacked directly on top of each other.
Exactly. That staggering, immense, groaning weight of a 25-car pileup aimed straight down into the earth. That is 50 kips.
Oh.
When an engineer looks at a relatively slim, 2-foot-wide concrete column in a parking garage and notes a 50-kip axial load, they are acknowledging that this column is silently, effortlessly holding up a fleet of 25 cars all day, every day.
Without moving a millimeter.
Without moving a millimeter.
That paints an almost terrifying picture of what our built environment is actually doing.
It does, doesn't it?
But here is where the plot thickens.
Yeah.
We just established that 50 kips is a massive amount of weight. But a building doesn't fail just because a weight is heavy.
That's a crucial point.
Right, because if I take those 25 cars and I park them spread out across an entire football field, the ground doesn't care. It easily supports them. But if I manage to balance all 25 cars on the head of a pin, the pin is going to instantly punch through the crust of the earth.
That is the fundamental difference between force and pressure. Or, in the language of structural mechanics, force versus stress.
Force versus stress. Okay.
Total force, the newtons or the kips, is only half of the equation. To truly understand if a material will hold or shatter, you must understand how sharp or concentrated that force is. We have to transition from total weight to force distributed over a specific contact area.
And the sources we're looking at make a massive point of this distinction. Specifically, looking at the force measurement documents, they practically draw a red line between N and N.
Because mixing them up is fatal. N is the total compressive force. It's the weight of the apple or the weight of the 25 cars.
Right.
But NN, newtons per square millimeter, fundamentally accounts for the size of the footprint. It measures the intensity of the force.
I actually have an analogy for this that I think isolates the true meaning of pressure versus force perfectly.
Oh, let's hear it.
Imagine you are standing in your living room barefoot. Let's say you weigh exactly 180 pounds. That is your total force. Gravity is pulling your mass down, and you're transferring 180 pounds of force into the floorboards.
Okay. And because you're standing flat-footed, that 180 pounds is spread out over the dozens of square inches that make up the soles of your feet. The intensity, the pressure on any single inch of skin is quite low.
Right. It feels completely fine. But now, imagine someone sneaks a single sharp little plastic Lego brick under your heel,
Oh, no.
and you step your entire 180-pound body weight down onto that one tiny brick.
The total force hasn't changed. You still weigh exactly 180 pounds.
Exactly. You haven't gained an ounce. Your kips or your newtons are identical. But the pressure, the emery, when your heel connects with the corners of that Lego, is suddenly absolutely astronomical.
Right, because the contact area has shrunk from the entire bottom of your foot down to a few square millimeters of hard plastic.
Yes. All 180 pounds of the Earth's gravitational pull is channeled through a pinprick. The pressure causes the biological material of your skin to physically fail. It pierces your foot. That is why it hurts.
It's an incredibly visceral way to understand structural stress. A steel beam or a concrete slab doesn't care how heavy the total building is. It only cares about how much force is being shoved through its specific microscopic footprint.
It's all about the footprint.
Yes. If the stress exceeds the material's internal capacity to hold its atoms together, it fails. And the metric unit we use to measure that internal threshold is the megapascal, or MPa.
Okay, what exactly is a megapascal?
We have to start with a pascal. A pascal is defined as 1 newton of force spread out over one entire square meter of area. So 1 n-meter.
Okay, wait, let's think about the physical reality of that. 1 newton is our medium-sized apple.
Right.
A square meter is roughly the size of a large dining room table.
Yes. So imagine spreading the weight of a single apple evenly across an entire dining table.
The resulting pressure is practically non-existent. It's a whisper.
Exactly. A single pascal is a uselessly small unit for engineering concrete and steel. So engineers use megapascals. Mega is the metric prefix for 1 million. So 1 MPa is 1 million pascals.
But mathematically, there is a beautiful shortcut here when we bring it back to millimeters, right?
Yes, there is. Because there happen to be exactly 1 million square millimeters inside a single square meter, the math simplifies perfectly.
Oh, that's convenient.
It is. 1 newton applied to 1 square millimeter, 1 millimeter, is mathematically identical to 1 million newtons applied to a square meter. Therefore, 1 n-millimeter 2 is exactly 1 MPa. They are one and the same.
Okay, so 1 n-millimeter is 1 MPa.
Yes. If a materials testing lab says a batch of concrete can handle 30 MPa, they are saying it can handle 30 newtons of force on every single microscopic square millimeter of its surface.
That's incredible. And in the American system, we use inches. So we look at PSI and KSI.
Right. PSI is pounds per square inch. KSI is kips per square inch. Since a kip is 1,000 pounds, 1 KSI is 1,000 PSI.
If an international team is collaborating, they have to jump between these systems flawlessly. Based on the steel construction tables we're looking at, 1 KSI converts to exactly 6.895 MPa, or 6.895 millimeter.
The precision there is non-negotiable.
So let's ground this in the real world. Let's look at the actual materials surrounding us. We have this fascinating specification sheet on concrete strengths from the sources.
Oh, the CoreTEF data.
Yeah. When I look at a concrete pillar, it just looks like a solid rock. How do engineers actually know what the PSI or the megapascal rating of a concrete mix is before they pour a building?
They know because they subjected a sample of it to absolute violence.
Violence.
Yeah. The global standard for testing concrete, it's called ASTM C39, involves taking freshly mixed concrete from the job site and pouring it into small cylindrical molds.
Okay.
They let those cylinders cure. Then they put them into a massive, heavily armored hydraulic press.
And they just crush them.
They systematically destroy them. The hydraulic press applies a perfectly vertical compressive force, slowly squeezing the cylinder from top to bottom. The machine precisely logs the total force, the kips or kilonewtons pushing down.
Wow.
Eventually, the internal friction of the concrete is overcome. The aggregate rock tears away from the cement paste, microcracks propagate at the speed of sound, and the cylinder violently fractures and shatters.
So they take the total maximum weight the machine applied right before the explosion, divide by the circular surface area at the top of the cylinder, and that tells you exactly how many pounds per square inch the concrete can take.
Exactly. And timing is everything here. Concrete doesn't dry like paint.
Doesn't.
No, it cures through a complex chemical reaction called hydration. The Portland cement reacts with water to grow tiny interlocking crystals that bind the sand and gravel together.
Oh, I had no idea it was crystal growth.
Yeah. And this crystal growth takes time. They might crush a sample at 7 days just to make sure the chemistry is working, but the official legal design strength of that concrete is based on how much it can withstand after curing for a full 28 days.
So translate that to my daily life. When I walk out my front door and step onto a standard residential concrete sidewalk, what kind of pressure rating am I standing on?
Well, basic flat work, like a patio or a sidewalk, is usually engineered for a compressive strength of around 2,000 to 3,000 psi.
Think about that. Every single square inch of that sidewalk, a little square roughly the size of a postage stamp, can hold 2,000 to 3,000 pounds of dead weight before it crumbles. A single square inch can hold an entire car.
It's remarkably strong stuff, but that's just the basement of concrete engineering.
Really?
Oh, yeah. If you are driving a heavy freight truck over the suspended slab of a highway bridge, that concrete is formulated to withstand at least 5,000 psi. And if you go into the subterranean parking levels of a massive 80-story skyscraper and look at the colossal columns anchoring the entire structure to the bedrock, those are poured with high-performance mixes that easily exceed 15,000 psi.
15,000 pounds.
Yeah.
7.5 tons, resting on a single square inch.
Yeah.
The chemistry required to make rock powder and water that strong is staggering. But, concrete is only meant to be compressed. What about steel?
Steel is an entirely different beast. It operates on a level of strength that requires us to move up from PSI to KSI just to talk about it efficiently.
Okay, let's look at the American Institute of Steel Construction sources. It says the workhorse of modern building is A36 structural steel.
Right, and the 36 in the name literally tells you its yield strength, 36 KSI.
Which means 36 kips per square inch, or 36,000 pounds per square inch.
Yes. And for the metric conversion, since 1 KSI is 6.895 MPa, A36 steel yields at roughly 250 megapascals.
This goes back to the hook we started with, the true meaning of 36 KSI.
Yes, the school bus.
Right. If I have a rod of solid steel that is exactly 1 inch wide and 1 inch deep, the cross-sectional area is 1 square inch. If I bolt the top of that rod to the ceiling and I hang weights from the bottom, I can hang 36,000 pounds from it. I can hang a fully loaded 40-foot school bus from a 1-inch rod of steel.
And the atomic lattice of the iron and carbon will just grip each other, stretch a tiny bit, and hold it.
And importantly, because 36 kC is the yield strength, the steel hasn't even permanently deformed yet. It is still behaving elastically.
Yeah.
If you take the school bus off, the steel rod shrinks back to its exact original length.
That physical reality changes the way you see the world, doesn't it?
It really does. When you look at the exposed steel beams in an airport terminal or the cables on a suspension bridge, you suddenly realize the astronomical forces they're wrestling with in absolute silence.
But, we have to expand our view again. We've talked about point loads, the car on the column, the bus on the rod, but real buildings don't just hold up single concentrated points of weight.
No, they hold up reality. They hold up floors full of thousands of walking people, roofs blanketed in blizzards, and walls battered by hurricanes.
Exactly.
So how do you even begin to measure a blizzard? How do engineers calculate loads that are spread out over vast, uneven areas?
This is where we introduce the concept of area loads and linear loads. In the U.S., the foundational unit for this is the PSF, or pounds per square foot.
PSF.
It is used to define how much weight is distributed over a two-dimensional surface like a floor or a roof.
Let's do the metric translation for PSF first, just to get it out of the way.
A good idea. Looking at the engineer's handwritten field notes we have, the conversion is clear. 1 PSF is equivalent to roughly 0.047 kilometer square meter.
Wait, kilonewtons per square meter?
Yes, kilonewton. And going the other direction, 1 kilometer equals 20.89 PSF.
So if I am looking at a residential building code and it mandates that the floor of a living room must be designed for a live load of 40 PSF, That means the structural engineer has to guarantee that every single 12-inch by 12-inch square of that floor can simultaneously support 40 pounds.
Exactly. Now, it doesn't mean there will literally be 40 pounds on every tile, but it accounts for the chaos of human habitation.
Right, like you might have a heavy oak bookshelf crammed into one corner, a grand piano in another, and 10 people clustered in the middle of the room for a party.
Exactly. Designing the entire continuous floor for 40 PSF ensures the overall floor system, the joists, the subfloor, the girders, can absorb that distributed chaos without sagging.
But human furniture is easy compared to nature. The Eurocode sources we have go into incredible, almost obsessive detail about environmental actions.
The Eurocode has to be obsessive because nature is relentless. Consider snow loads.
Oh.
The code denotes this as the variable, the characteristic snow load on the ground. You can't just treat snow like a layer of feathers.
Because it melts, right?
Well, when snow lands on a roof, it undergoes thermodynamic changes. The bottom layer melts slightly from the heat of the building and refreezes into solid ice. More snow piles on top, compressing the lower layers, radically increasing the weight density.
Oh, so it gets heavier the longer it sits there.
Yes. The Eurocode forces engineers to calculate the pitch of the roof, the local climate data, and the risk of drifting snow piling up against parapets. A seemingly innocent winter storm can spread thousands of kilonewtons of crushing force across a massive warehouse roof.
And wind is even more complex, because wind isn't just a physical object resting on the building. It's fluid dynamics.
Wind is terrifying because it attacks the building from every direction at once, and it doesn't just push, it pulls.
Wait, it pulls?
Yes. The Eurocode calculates wind loads using external pressure coefficients and internal pressure coefficients.
Pull that apart for me. How does wind pull on a building?
It's the Bernoulli principle, exactly like the wing of an airplane. When a high-speed wind whips over the flat or slightly pitched roof of a building, the air accelerates.
Right.
Fast-moving air creates low pressure. It literally creates a vacuum effect suction on the exterior of the roof. Meanwhile, the static, calm air inside the building is still at normal atmospheric pressure.
Oh, I see where this is going.
So the inside air is actively pushing up against the ceiling, while the wind outside is trying to suck the roof off into the sky.
The net pressure is the difference between the inside pushing up and the outside pulling up.
Exactly.
If the engineer doesn't calculate that uplift force in PSF or kRNMAU and secure the roof to the walls with heavy steel hurricane ties, the entire roof assembly will rip clean off the structure and fly away.
It happens all the time in severe storms when older buildings weren't designed to the modern code. The invisible fluid of the atmosphere is incredibly powerful. The code even dictates calculations for fire load densities.
Fire has a load. Does heat weigh something?
In this context, load refers to energy. Fire loads are calculated based on the chemical potential energy of the combustible materials inside the building: wood, paper, plastics.
Okay.
It's measured in energy released per unit of floor area. Engineers must calculate how hot a fire will burn and for how long, so they can specify concrete cover thickness and fire-resistant steel coatings that will survive the exact thermal energy of that specific fire.
Every conceivable variable of reality is quantified. Now, there is another unit in those field notes that bridges the gap between an area load and a point load: KLF. What is the physical reality of a KLF?
KLF stands for kips per linear foot. You can actually see in the notes the engineer hastily scribbled KOOF before aggressively correcting it to KLF. It is the universal language for sizing structural beams.
Okay, let's visualize this. Imagine you have a massive, open-concept ballroom, no columns in the middle, just a giant 50-foot-long steel beam running across the ceiling, carrying the weight of the floor above it.
Okay, I picture it.
The weight of that upper floor isn't resting on the center of the beam like a single parked car.
No, the floor joists are resting on the beam every 16 inches along its entire length. The load is continuous, so engineers calculate it as a linear load.
So if the math says the beam must carry 3 KLF, that means for every single 12-inch slice of that beam, every linear foot, it is feeling 3 kips or 3,000 pounds of force pushing down.
Right. So a 50-foot beam carrying 3 KLF is holding up a total of 150,000 pounds. But it's feeling it like a heavy, continuous blanket, not a hammer blow to the center.
Precisely, which dictates how the beam bends and where it needs to be thickest. But, none of these load calculations, not the PSF of the snow or the KLF of the beam work if the engineer messes up the physical geometry of the building.
Which brings us to the dimensions. Scaling space. Because a mathematical error in converting dimensions between the metric and American systems isn't just a bad grade on a test, it results in real-world structural failure.
We have to move smoothly from one-dimensional lines to two-dimensional areas to three-dimensional volumes.
Let's run the exact conversions requested, starting with 1D lines, converting inches and meters to feet.
Okay.
For U.S. customary, converting inches to feet is simply dividing by 12, so 1 inch is mathematically 0.0833 feet.
Simple enough.
When jumping the metric divide, the handwritten field notes show a practical shorthand. 1 meter is roughly 3.33 feet, though the exact conversion used in precise calculations is 3.2808 feet. Going the reverse way, 1 foot is exactly 0.3048 meters.
That's 1DA, just drawing a straight line on a blueprint. Now we step into 2D area. Square meters to square feet.
When you move to 2 dimensions, you have to square the conversion factor. A square meter is an area 1 meter wide by 1 meter long. Since 1 meter is roughly 3.28 feet, you multiply 3.28 by 3.28.
Which is?
The result is 10.76. Therefore, 1 square meter is equal to 10.76 square feet. Okay, 1 esquire at 10.76 with the feet. And now the terrifying jump into 3D volume, cubic meters to cubic feet.
You cube the conversion factor, 3.28 times 3.28 times 3.28. The result is 35.315. So 1 cubic meter is equal to 35.315 cubic feet.
I want to stop and highlight the physical reality of what you just said. This is the square cube law in action, and it is fascinating because the human brain really struggles to comprehend exponential growth in 3D space.
Walk us through how you visualize it.
If I draw a line on the ground that is 1 meter long, and next to it a line that is 3 feet long, they look almost identical. A meter is just a tiny bit longer than a yard. They are comparable human scale lengths.
But the moment you expand those lines into three-dimensional boxes, the illusion shatters. A cubic foot is a box roughly the size of a milk crate. A cubic meter is a box roughly the size of a commercial washing machine.
It's a huge difference.
1 cubic meter holds over 35 cubic feet inside it. A small change in 1D length balloons into a massive cavernous 3D volume.
That exponential ballooning effect is exactly why bulk weight density is one of the most critical numbers an engineer must calculate. When you scale up a material from a tiny sample to a massive building component, the weight multiplies at a terrifying rate.
Think about concrete. A single cubic foot of standard concrete, our milk crate, weighs about 150 pounds. 2 strong people could lift it.
Okay.
But if you accidentally scale your drawing in meters instead of feet, and you pour a cubic meter of concrete, because it is 35 times larger in volume, that washing machine-sized block weighs over 5,200 pounds.
2.5 tons.
Exactly. If an engineer confuses feet and meters, a beam that was supposed to hold 150 pounds is suddenly asked to hold a truck. The structure immediately collapses under its own dead weight.
Which is why the Eurocode is so unbelievably pedantic about defining bulk weight density. The code states that density calculations must account for the normal distribution of microvoids, voids, and pores inside the physical material.
Wait, they calculate the air bubbles.
They absolutely have to. You cannot just calculate the atomic mass of pure limestone and pure steel. Concrete on a job site isn't perfect. As it cures, microscopic air bubbles and water pores are trapped inside the matrix.
I guess that makes sense.
Wood has varying moisture contents and cellular voids depending on the humidity. The Eurocode demands that engineers use the real-world on-site bulk density of the material, voids and all.
Because when you multiply a material by tens of thousands of cubic meters, every fraction of an ounce of trapped air drastically changes the final dead weight pulling down on the foundations.
Exactly. It all adds up.
Okay, we have laid down all the puzzle pieces. We understand the unyielding pull of gravity in newtons and pounds. We scaled up to kilonewtons and kips to measure the crushing weight of 25 cars.
We did.
We shrank down to square millimeters and inches, MPa and KSI, to understand how sharp pressure destroys materials. We spread that weight across floors with PSF and ran it along beams with KLF, and we locked down the sheer exponential horror of scaling up volume.
We have the entire physical and mathematical vocabulary.
Which brings us to the grand finale, the structural mechanics. What is physically happening inside the atomic structure of the steel and concrete when all of these forces are finally unleashed on them?
To understand the battle inside the material, we have to synthesize everything using the structural mechanics lecture notes. The entire field of structural engineering boils down to a conversation between 2 fundamental concepts: stress and strain.
We know stress. We've defined it deeply. Stress is the cause. It is the applied force divided by the area. It is the school bus hanging from the steel rod, the MPa, the KSI. Stress is the punch.
Correct. Strain, on the other hand, is the effect. Strain is the physical geometric response of the material to the stress.
How do they define it?
The lecture notes define strain as the deformation per unit length. Mathematically, it is the change in length divided by the original length. It's a ratio.
Meaning, if I have a steel beam that is 100 inches long, and the stress of the building stretches it until it is 101 inches long, the beam elongated by 1 inch.
Great.
So 1 divided by 100 is 0.01. The strain is 0.01. It is dimensionless. Stress is the punch. Strain is the bruise.
And the law that dictates how materials bruise is called Hooke's law. Hooke's law states that for perfectly elastic materials, stress is directly proportional to strain.
Elastic materials, we touched on this, but it's hard to visualize steel as elastic. I think of a rubber band. You pull it, it stretches. You let go, it snaps back.
But that is exactly what the steel is doing. Within a specific window of force, the crystalline lattice of iron and carbon atoms acts exactly like a rigid rubber band.
Really?
Yes. The atoms pull slightly away from each other, but the electrostatic bonds between them hold strong. When you remove the load, those atomic bonds pull the atoms right back to their starting positions. The beam shrinks back to its original length.
But if I pull a rubber band too far, it turns white, it gets weirdly stringy, and it doesn't snap back. It's ruined.
You have exceeded the elastic limit. To truly understand how a building survives, you have to look at the stress-strain curve. This is a literal graph that engineers use to chart the entire lifespan of a material as it is slowly destroyed.
Walk us through the narrative of that graph. Imagine we have a thick rod of structural steel locked into a massive industrial pulling machine.
As the machine turns on and begins to pull, we enter the elastic range. On the graph, this is a perfectly straight diagonal line angling upward. As the machine increases the pulling force, the stretching increases proportionally. It is perfectly balanced.
The steel is fighting back. It's a rubber band.
Exactly. But eventually, the machine pulls so hard that it reaches a critical threshold on the graph called the yield point.
For our A36 steel, this is that 36K Sauer's mark, 36,000 pounds per square inch.
Yes. The moment the stress hits 36,001 pounds, the physical reality inside the steel fundamentally changes. The atomic bonds can no longer stretch. They begin to slip. Entire planes of atoms slide past each other. The material enters the plastic range. The steel permanently deforms. If you turn the machine off now, the rod will be permanently longer than when you started. It has yielded.
But the building hasn't collapsed yet. Yielding isn't breaking.
Far from it. In fact, as the planes of atoms slip, they actually tangle up with each other, a process called strain hardening. The steel becomes even harder to pull.
Oh, that's interesting.
The machine has to exert massive amounts of stress, climbing higher and higher up the graph until it reaches the peak, the ultimate stress.
This is the absolute maximum limit state load the material can possibly take. It's giving everything it has.
And right after it hits ultimate stress, the material realizes it has lost the battle. Something deeply dramatic happens physically. The steel begins necking.
Necking, like the neck of a bottle.
Like an hourglass. If you watch the steel rod right in the middle, the metal suddenly starts to narrow rapidly. The cross-sectional area shrinks as the atoms flow like incredibly thick putty. Because the area is rapidly shrinking, it actually requires less total force from the machine to keep stretching it. The line on the graph dips downward. The neck gets thinner and thinner and thinner until
Rupture.
it snaps. The atomic bonds are completely severed.
That is the lifespan of metal in tension. But buildings aren't just pulled apart. They are mostly crushed under compression. Which brings us to a phenomenon in the lecture notes that completely blew my mind. Poisson's ratio.
Poisson's ratio. I want to spend time here because this explains so much of what we actually see on a construction site.
If you take a block of soft modeling clay and you squish it down with your hand, what happens to the shape of the clay?
It gets shorter, but the mass has to go somewhere, so the sides bulge outward. It gets fatter.
Exactly. Volumetric conservation.
Right.
When you compress a material linearly, it expands laterally.
Right.
Poisson's ratio is the mathematical measurement of how much a specific material bulges outward when you squish it downward. Every material has one. Rubber bulges a lot. Cork barely bulges at all, which is why you can jam a cork into a wine bottle. But concrete bulges too.
It does. When a concrete column is supporting 50 kips of weight, it isn't just compressing vertically. The internal stress is actively trying to burst the column open from the inside out. The lateral strain is pushing against the outer edges of the concrete.
This changes everything. When you drive past a construction site and you see them building a concrete column, They don't just pour the concrete.
No, they don't.
They build a skeleton of steel rebar first. They have vertical bars, but then they wrap those vertical bars in hundreds of horizontal steel hoops, tying it all together into a tight cage.
Those hoops are called transverse ties, and their primary job is to fight Poisson's ratio.
That makes perfect sense.
As the concrete tries to bulge outward under the crushing weight of the building, those steel rings act like a corset, physically restraining the lateral strain, holding the microscopic structure of the concrete together so it doesn't shatter laterally.
It is a perfectly choreographed dance of materials. The concrete resists the downward squish, and the steel hoops resist the outward bulge.
And the overall stiffness of the material, how much it squishes or stretches in the first place, is governed by one final property: Young's modulus.
Young's modulus, or the modulus of elasticity, is essentially a measurement of pure stiffness. It is the ratio of stress divided by strain within that elastic rubber band zone.
Exactly. A material with a massive Young's modulus, like structural steel, is incredibly rigid. It takes an enormous amount of stress to create a tiny bit of strain.
And a material with a low Young's modulus, like rubber, requires very little stress to create a massive amount of strain.
So we have force, we have area, we have length, and we have material stiffness, which is Young's modulus. In the lecture notes, there is a master equation that ties every single one of these concepts together into a single mathematical sentence.
You are looking at the fundamental equation for axial deformation. Delta L equals PL over AE.
Let's break this equation down because it perfectly summarizes the entire deep dive.
Okay, delta L is the answer we are looking for. It is the change in length. It tells the engineer exactly how many fractions of an inch a column will squish or a cable will stretch.
And that change in length is dictated by a fraction. On the top of the fraction, the numerator, we have P times L.
P is the total applied force. The newtons, the kips, the 25 stacks cars.
Right.
L is the original length of the column. So the top of the fraction represents the destructive reality of the world. A massive weight acting over long distances trying to create maximum deformation.
But fighting against that destruction is the denominator, A times E.
A is the cross-sectional area. The square millimeters, the square inches, making the column wider, spreads out the force and lowers the stress.
And E is Young's modulus, the inherent atomic stiffness of the material itself.
Exactly. Force and length, PL, are actively trying to stretch or crush the building. Area and material stiffness, AE, are actively fighting to hold it together.
Delta L equals PL over AE is the ultimate structural tug of war. By perfectly balancing those four variables, an engineer can guarantee that the building will breathe, flex, and survive without ever leaving its safe, elastic limit.
So if I'm tracking this incredible journey, we started with a single Newton, realizing it was just the weight of an apple resting in the palm of your hand.
Right?
We scaled that tiny force up to the massive kips and kilonewtons required to represent the crushing weight of cities. We learned that total weight doesn't matter as much as the sharpness of the footprint, transitioning from force to the intense pressure of megapascals and KSI, proving that biological skin and structural steel both fail when the stress is too localized.
We covered a lot of ground.
We spread those loads across the environment with PSF for snow and wind, translated 1D lines into terrifying 3D volumes, and finally watched the atomic lattice of materials fight back elastically in the delta L equation.
We really have translated the alphabet soup back into the physical world.
We have. And it changes the way you interact with your environment. Which leads me to a final thought. I want to leave you, the listener, to explore on your own.
I'm ready for this.
The next time you walk into a massive, modern, open concept space, maybe an airport terminal with a soaring glass roof, or the subterranean levels of a massive parking structure, stop for a moment.
Just take a look around.
Look at the seemingly quiet, static columns anchored into the floor. Do not just see a piece of rock or a painted steel tube. Visualize the invisible, violent reality happening inside that column at that exact second.
It's intense.
Think about the thousands of kips of gravitational pull, the weight of entire fleets of cars and acres of snow bearing down continuously. And against that, visualize the atomic lattice of the steel and the crystalline structure of the concrete, fighting back on every single microscopic square millimeter.
The Poisson effect in action.
Think of the concrete trying to bulge outward and the hidden steel rebar rings choking it back into place.
Yeah.
You aren't just standing in a quiet room. You are standing inside a roaring, perfectly balanced mathematical engine, and it is fighting to keep you safe every second of the day. Thanks for taking this deep dive with us.